As we are starting our third lecture, I think it's a good moment to pause and think a little bit about what we said so far, and I would like to outline for you where we are going in what is my narrative. So essentially, I started by telling you that quantum physics is a different kind of probability theory. We have to add amplitudes, so they take mod squares, and then it does make the difference, because when we see things happening in what looks like a mutually exclusive ways, we don't add probabilities, we kind of correct the additivity axiom by Kolmogorov by this one extra interference term. And this interference does make all the difference. So all quantum physics is essentially about studying these interference terms, because this is exactly where the departure from the classical theory of probability is. And so indeed, without this interference term, there wouldn't be quantum physics, there wouldn't be this lecture about quantum information science, there wouldn't be any excitement about quantum computing and quantum cryptography, you name it. So essentially, we are studying this interference term in all kind of disguises. You know, you may not see it right away, but when you look very carefully, you see that what is really exciting is this interference term. And remember, I gave you a generic example. We went to the simplest possible state, physical system that is a quantum bit that has only two distinguishable states. We can distinguish those two states, and we label them 0 and 1, and we run interference sequence on a qubit. If you look at this diagram, you can see that there are indeed trajectories, internal trajectories. So for example, if you want to see the qubit moving through initial state 0 to some final state, say 0, and we want to know what is the probability that the qubit will end up there, then in this dual ray diagram here, you draw possible paths. You say, well, qubit can go this way, or the qubit can go also this way. We attribute probability amplitudes to those two different paths, then we add them together, take mod square, and calculate probabilities. Usually we don't do things this way because it's too complicated. Instead, we draw circuit diagrams where we say, and you know, this is the golden circuit diagram, the one thing that you will see over and over again, and this will be sort of the main point again of our investigations in a moment. Essentially, you know that I told you that when we start in state 0, and we go through a sequence of what is called the Hadamard gate, the phase gate phi, the Hadamard gate, then the state of the qubit at the output can be written as cos phi over 2, state 0 minus I sine phi over 2, state 1. And then the probabilities, of course, are given by mod square when we ask the question, what is the probability of finding the system of our qubit at the output in state 0, then it is cos squared phi over 2. And the probability, of course, of finding it in state 1 is sine squared phi over 2. So that's the story so far, right? So we are here, and of course, you know, I was also telling you about some embellishment on this theme, that apart from this quantum interference, I wanted you to visualize this quantum interference in terms of rotations on the Bloch sphere. Remember, we can always represent the state of a qubit in terms of a Euclidean vector on a Bloch sphere. Then I wanted you to see unitary operations in terms of rotations of those Bloch vectors. So you can then look at this thing here and say, well, yes, I understand what it is. This phi is a rotation about the z-axis by phi. The Hadamard is a rotation that swaps x and z-axis. So altogether, this combination here is in fact a rotation about the x-axis by phi. So that allows you to write certain formulae even without doing the calculations. So now I'm going to introduce, well, you expect, you know, we're talking about one qubit. Well, now we're going to talk about 2 qubits or more. So I'm going to introduce another qubit. So another qubit will appear here. Let me just draw another line here. So now we will be having that kind of system, so that we have one qubit here, another qubit here, and I let those two qubits interact. So at some point in between the Hadamard gate, they will interact. That will bring another interesting feature to our discussion here. When they interact, they get entangled. So entanglement will be another feature of quantum physics that you will see. Again, think about it this way: if quantum physics is another kind of probability theory, so entanglement will then be about the correlations between subsystems, between, say, for example, two qubits. And because we have a different kind of probability theory and we calculate probabilities in different way, then you may expect that those correlations will be different if they are calculated in a quantum way. And indeed, that is the case. So the new thing that I'm going to introduce now is entanglement. Now, and quantum entanglement can actually play both positive and negative role. It will in fact play both positive and negative role in our discussions. So if you have two subsystems and they get entangled, and you can control both of them, then it's a good thing. So then entanglement is your friend in this case. And that will lead into wonderful discussions about Bell inequalities, quantum cryptography, in fact, quantum computing and quantum crypto, and all kind of wonderful features. So that assumes that we can control entanglement, so that we have access to entangled subsystems and we can control them, we can operate them, we can manipulate them, we can measure them. So that's a good thing. Once we have this control, entanglement is extra resource, something that will allow us to really take this multi-particle quantum interference to give it a wonderful application and use it. However, if we have situations where we have two entangled subsystems, but we can only control one of them, so that is usually the case that we have our qubit and there's everything else, the rest of the world. And we cannot control the rest of the world. We wish we could, right? But we cannot. So we control only this qubit. But if this qubit gets entangled with something that we cannot control, that's, the entanglement in this case is not our friend, it's our enemy. In quantum crypto, it could be an adversary. It could be someone who is trying to eavesdrop on your crypto system. You cannot control that guy, right? So the question then is, what can you do? How can you handle situations like this? So that will lead us to discussion of decoherence, and also we'll be talking about error correction. It's going to be quantum error correction. So we will try to do something about it. The entanglement is going to mess up. In fact, you will see in a moment that there is a trade-off between, in this particular scenario, between quantum interference and the degree of entanglement. So when we have the two subsystems, one qubit and another qubit, if they are not entangled, that this one has this nice pure interference that you saw. But if they get entangled, then this entanglement has a negative impact on quantum interference. It's just, and there are many ways, of course, of telling you the same story. I mean, it's one way is to say that this another subsystem is just learning which particular path in this diagram here this system is taking. So the act of entanglement is inherently connected with the act of measurement. So that's something that we also touch upon later on. So here we are. Quantum interference. Now comes few subsystems, quantum entanglement. And it can play both positive or negative role And we will be talking about both. We will talk about quantum computation and quantum cryptography, where quantum entanglement is our friend. And then we'll talk about decoherence, where quantum entanglement is certainly not our friend. But then, you know, it's not like a gloomy story, because we also have quantum error correction, so we can do something about it.